In themselves, lateral and vertical variations in apparent conductivity have been used to infer changes in soils and soil properties and to detect surface anomalies. One of the tools used to measure electrical conductivity is the ground-penetrating radar. The purpose of this video is not to show the viewer how to use ground-penetrating radar, but rather to introduce the principles and concepts of using and interpreting ground-penetrating radar.
The radar circuitry inside the ground unit generates a sequence of trigger pulses. These pulses are sent via the control cable to the antenna, where each trigger pulse is transformed into a bipolar transmit pulse. The transmit pulses are then directed into the subsurface by the antenna, which is pulled along the surface. The energy is radiated in a conical pattern, roughly 90 degrees front to back and 60 degrees side to side. The transmit pulse encounters different materials in the subsurface, each with different dielectric properties. Where the different subsurface materials meet or interface and the dielectric constant changes, some energy is reflected back to the subsurface and detected by the receiving antenna. The received signals are then sent back to the control unit where they are processed. The data are displayed on the color monitor and can be stored on the internal hard drive for later playback or printed on a thermal plotter. The horizontal axis on the display represents the distance along the ground surface. The vertical axis indicates the time it takes for the transmitted pulses to enter the ground, reflect from an interface, and return to the antenna receiver. This is called travel time and can be converted to depth once the velocity of the radar pulses is known. The strength of the return pulses determine the darkness or color on the display when in line scan format. How well ground-penetrating radar, or GPR, will solve a particular problem at a certain site mainly depends on two electrical properties of the subsurface materials: electrical conductivity and relative dielectric permittivity, or the dielectric constant. These properties are important to understand in order to acquire good data. Let's first look at the dielectric constant. This is a measure of the capacity of a material to store a charge when an electric field is applied. Different subsurface materials have different dielectric constants. The value of the dielectric constant ranges between 1 for air and 81 for water. You'll find a table in your SIR 2 manual that gives the approximate values for a variety of typical subsurface materials. At the subsurface interface, some part of the radar signal passes through the interface to the underlying material, while some is reflected back to the antenna. How much signal is reflected and how much passes through depends upon the difference of the dielectric constants between the two layers. In GPR, it is important that the change in the dielectric constant occurs over a short distance in order to produce a good reflection. If the dielectric constant changes gradually in the subsurface, reflections from the boundaries will be weak, discontinuous, or non-existent. For example, the ability to detect a water table is highly dependent upon the sharpness of the water boundary. A fine-grained sand layer could have steadily increasing water saturation with depth. In other words, no sharp water table boundary. This gradual change from dry to saturated sand is barely detectable. However, coarse-grained sands would have a sharp water table boundary, which would be easily detectable. The next property to understand is electrical conductivity, a measure of the ability of a material to conduct an electric current. This will determine the depth of penetration of the radar signal. The lower the conductivity of the materials, the deeper the radar signal can penetrate. Conductivity is controlled by the water, mineral, and clay content in the subsurface. The conductivity of water-saturated clay is high enough that it will greatly limit the penetration of the radar signal. Salt water is so highly conductive, it effectively blocks the radar signal from penetrating. On the other hand, dry sand, limestone, granite, asphalt, and concrete have low conductivity and allow good radar penetration. The chart in your manual also lists the electrical conductivity of typical subsurface materials. The depth of penetration is also dependent on the antenna selected. GSSI manufactures several antennas with ranges from 20 megahertz to 2.5 gigahertz. The lower the frequency, the greater the penetration depth. The higher the frequency, the better the resolution.